Well, good evening, friends. Thanks for joining me tonight for our live lecture here for Calculus 2. I really believe that the strike is almost over. I also recognize that this has been a challenging time for everybody, and I strongly appreciate your patience. If you are in my class, I will again be in SEO 430 tomorrow at 3 o'clock. I'll bring a worksheet to give you a chance to practice some of these concepts. So hopefully you're available. Hopefully you're on campus tomorrow. If so, please stop by SEO 430 at 3 o'clock for a work session. All right. So as you can see, today's lesson's on parametric equations. Let's just do a quick review of our Maclaurin series before we get into today's lecture. The thing I want you to remember is our three basic versions, right? Our Maclaurin series, or actually Taylor series centered at 0. We have three things that you want to try to memorize, right? We have e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus ... Cos x, even powers alternating, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus ... And sine x, odd powers alternating, x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7th over 7 factorial. So I really think you should memorize those. They are Maclaurin series. A Maclaurin series is a Taylor series centered at 0. And our last video on working with Maclaurin series showed how you can do some analysis. I don't know. If we want to go ahead and construct a new Maclaurin series from this, we can. For example, if I want to get a Maclaurin series, a Taylor series centered at 0 for cos 2x, just replace all the x's with 2x. So 1 minus 2x squared over 2 factorial plus 2x to the 4th over 4 factorial minus 2x to the 6th over 6 factorial plus ... And for example, if I had given you this, if I asked you what is 1 minus pi over 3 squared over 2 factorial plus pi over 3 to the 4th over 4 factorial minus pi over 3 to the 6th over 6 factorial plus ... You look at something like that and you say, oh, I sort of recognize that. You know, what is that series? It's cosine, even powers alternating. X is replaced with pi over 3. So this equals cosine of pi over 3, which is a half. So if you know those three basic Taylor series, e to the x, cos x, and sin x, that's very helpful. I will challenge you on one thing, though. There is a really nice fact that we can ix, namely the following, and I'll try to get this to focus if I can. There we go. E to the ix is equal to cos x plus I times the sine of x. What is that? Well, what is e to the ix? E to the ix is 1 plus ix plus ix squared over 2 factorial plus ix to the 3rd over 3 factorial plus ... Cos x, you know what cos x is, right? You know what cos x is. You also know that I squared is -1. So if we're looking at how this behaves, e to the ix is 1 plus ix, that's minus, because I squared is -1, x squared over 2 factorial. I cubed is -I, so minus I times x cubed over 3 factorial plus ... That's e to the ix. Cos x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus ... And I times the sine of x is what? Is I times the odd powers, x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus dot, dot, dot. So see if you can convince yourself cos x plus I times the sine of x will equal e to the ix. So yeah, it's a nice little thing. And if we look at that, e to the I pi, I, of course, is the square root of -1. If you're not familiar with that, I squared is -1. E to the I pi is cos pi plus I times the sine of pi. So e to the I pi is what? Is cosine of pi is -1 plus 0, which tells me e to the I pi plus 1 equals 0. This rule is credited to Euler. And again, just a nice little fact, but I want you to recognize 1, 2, 3, 4, 5. The 5 most important constants in mathematics are showing up in this formula. 0 and 1, certainly very, very important constants. E, I, square root of -1, and pi all show up in one equation. So that's a nice little application of our Maclaurin series, our Taylor series centered at 0. So add that fact to your collection of things you know. If you're interested, come and talk to me. I'll show you how we can use this rule to prove most of our trig identities, at least our challenging ones, like cos of a plus b and sine of a plus b. But tonight's lesson is on parametric equations. So let's go ahead and jump to those. And what are we going to have? What are we going to start with here? What do these parametric equations look like? And I apologize for that shadow. Slide over things over a little bit better, maybe. So here we go. Parametric equations. What do they mean? What do they look like? And what kind of analysis can we do with them? So here's an example. We have x of t, which is 3t minus 1, and we have y of t is t squared plus 4. Now, we don't graph t, but we use t. We think of t as time, and then we graph the points x, y. So I'm going to look at various values of t. For example, if t is -2, 3 times -2 is -6, minus 1 is -7. That's x. Y, -2 squared is 4. 4 plus 4 is 8. So we start at -2, 8. If t is -1, 3 times -1 is -3, minus 1 is -4. -1 squared is 1, plus 4 is 5. Next up, we have 0. 3 times 0 minus 1, minus 1. 0 plus 4 is 4. How about 1? 3 times 1 is 3. 3 minus 1 is 2. 1 plus 4 is 5. And we'll do one more point just to kind of get ourselves an idea where we are here. If t is 2, 3 times 2 is 6. 6 minus 1 is 5. 2 squared is 4. 4 plus 4 is 8. So parametric equations, we have a variable t that we think of like time. At time -2, we're at the point -7, 8. At time -1, we're at the point -4, 5. So if I want to graph this, what does that look like? X goes to -7, 1, 2, 3, 4, 5, 6, 7. It goes to 5. 1, 2, 3, 4, 5. The y values are all between 4 and 8, so I don't need a whole lot of y values. 1, 2, 3, 4, 5, 6, 7, 8. So I start at the point -7, 8, which is somewhere around there. Then we go to -4, 5. -4, 1, 2, 3, 4, 1, 2, 3, 4, 5. I don't know, somewhere around there. Then we go to -1, 4. Then we go to 2, 5. Then we go to 5, 8. So as t is increasing, the function goes this way. We assume we have arrows going that way, but I put little arrows here, though, to tell me as t is increasing, that's where things are headed. That'll be important for us when you get to multivariate calculus. We'll need to know the orientation of functions. Now, here's the thing. can I express this graph as y is a function of x? So goal, rewrite as y is some function of x. To do that, the process we're going to use is called eliminating the parameter. Eliminating the parameter. So let's do that. Thank you for the like so early in the discussion. So let's go ahead and eliminate the parameter, see what we get. Let me explain to you what I mean by that. So we have x is 3t minus 1, and y is t squared plus 4. I want to write some equation with x and y. So yeah, maybe y is f of x may be too ambitious, or some equation in x and y, in other words, with no t. So what I'm going to do here is I'm going to wind up solving for t. So if I solve for t here, add 1 to both sides, x plus 1 is 3t, and divide 3 from both sides. So I get x plus 1 divided by 3 is t. And now I'm going to go ahead and plug that in. Plug that in where? We'll plug that in here for y. So I indeed will get y as a function of x. And I will have eliminated the parameter. So I get y is t squared, x plus 1 over 3 squared plus 4. And I could do all kinds of algebra to make that look a little bit cleaner, but I'm not terribly interested in doing that, so I think I will pass. Okay, so let's take a look at another one. I'm going to give you a parametric equation. We want to think about what the graph looks like, and then we'll want to eliminate the parameter to try to express it as some equation in x and y. So here's what we're going to get. We're going to take a look at x is cosine t, y is sine squared t. X is cosine t, y is sine squared t, and we are interested in this as we go 0 less equal t less equal pi. So what is that going to look like? What will the equation be when we eliminate the parameter? Now, to do this, we've got to keep in mind one of our favorite identities. And maybe it's obvious that the identity I want to use here is cos squared t plus sine squared t is 1. Well, knowing that, cos squared t, cos t squared, that's just x squared. So this first piece becomes x squared. Sine squared t is y. And I have successfully eliminated the parameter. That answer is fine. X squared plus y equals 1 would be a fine answer for this. But I could also go ahead and solve for y, and I could say y is 1 minus x squared. But again, only for what values t goes from 0 to pi. So if we would graph that, we're going to get a portion of that parabola, not the whole thing. I don't know if you can see the graphing calculator on there. You do have a parametric mode. Again, I doubt you can see that. You have a parametric mode there. So I'll just take a quick look. And I can go ahead and I can say x is cosine t, which you could sort of see. And y is sine squared t, which I have to do this way. Sine t squared. And then t is ranging from 0 to pi. So window, t is going from 0 to pi. I don't know about the other stuff. I like to start with zoom decimal if I can. Let's see what the graph looks like. Portion of a parabola, right? Y equals 1 minus x squared. You can't quite see that, but indeed it's the portion of the parabola that goes like this. Obviously, cosine of 0 is 1, cosine of pi is -1, so you can see that's our range of values for that one. Okay, let's do another one, same kind of argument. We want to go ahead and eliminate the parameter. That's what this would be called. So I will do the following. Just so we're clear on our directions, eliminate the parameter. And I have x is e to the 2t, and I'll have y is equal to e to the t minus 6. So we've got to think of some way for us to do this. And I think e to the t is going to be the key idea. First of all, e to the 2t means e to the t to the second power. We know that. If you raise a power to a power, you multiply the exponents. Over on this side, I'll add 6 to both sides. Y plus 6 equals e to the t. So you can see what I can do. I can substitute y plus 6 in for e to the t. What that will give me is x equals y plus 6 squared. And we'll try again. Let's take a look at our graphing calculator. We can do that. So we'll take x is e to the 2t, e to the 2t, and y is e to the t minus 6, e to the t minus 6. Whoops. I don't know what my window should be here because I didn't tell you in the problem. So I can just make one up. Maybe I can go minus 10 to 10. What does our graph look like? Can we see anything? Not really. Let's zoom it out once. It'll give us a better idea. Interesting. I hadn't thought about that. I'm not sure you can see this. Nah, not really. But what I'm getting is I'm only getting half of the parabola. So the shape of this, that's my xy axis. The shape looks something like this. Which is kind of interesting. So I want you to think about why that would be. We have no negative x values, and x is e to the 2t. All of my x values have to be positive. Except we would think that we would get something like this for a parabola, but why are you only getting this upper piece? Only one y value, e to the t minus 6. We don't have two y values for a single t value. So indeed, we only get that piece of the parabola, which to me is kind of interesting for us to work with. So eliminating the parameter, drawing graphs is a skill that you're going to want to have. Okay, one of our favorite kind of parametric equations is for a circle. So let's take a look at that if we can. So let's remember what an equation of a circle is. So this label on this part of the lesson will be circles in parametric form. So we know our general form of a circle centered at the origin is x squared plus y squared equals r squared again. Circle centered at the origin. But this is reminiscent of something, namely cos squared t plus sine squared t is 1. Or if you like, cos t quantity squared plus sine t quantity squared is 1. We know that is our favorite identity from pre-calculus. So how do we equate these two lines? We look at the first one and we look at the last one. We're trying to think about a circle centered at the origin with radius 1 in this case. What would that be? Well, x would have to be cosine t, and y would have to be sine t. And this is exactly what we said back in pre-calculus when we're talking about the unit circle. Except we're using t here instead of theta. Let me show you what I mean. So this is a unit circle. So this is a circle whose radius is 1. If I pick a point on that circle, if this is t in radians measured from the x-axis, the x value, of course, is cosine t, and the y value is sine t. So this sort of connects those two ideas, this unit circle idea that we use so much in trigonometry, together with our parametric form that we're studying in tonight's lecture. That to me is kind of interesting. But we can generalize this idea. So let's get away from centered at the origin with radius r, and let's do it in general. So we'll take a look at x minus h squared plus y minus k squared equals the radius squared. So this is a circle centered at HK, circle where the center is HK and the radius is R. So we know that. Now, how can we use what we did up here to make sense of what we have down here? Well, if we're going to use our favorite identity, I have to have it equaling 1. So to do that, I've got to divide both sides by r squared. So we'll take x minus h squared over r squared plus y minus k squared over r squared is 1. And we're getting closer to what we want here. But I'm going to rewrite this now as x minus h over r squared plus y minus k over r quantity squared is what I should have said, equals 1 squared. If that's important, maybe not. Now we want to connect this to our favorite identity, our favorite Pythagorean identity, which we used in our discussion up here. Remember? What did I say? Cos squared t plus sine squared t is 1. Cos t quantity squared plus sine t quantity squared is 1. How does that relate to this? Can we connect this idea with this idea? I hope you can. So we're seeing how to construct a parametric representation for any circle. So using our identity, cos t quantity squared plus sine t quantity squared is 1 tells me what? How do I equate these ideas? Well, I say that cos t is x minus h over r, and sine t is y minus k over r. And what I have to do now is I've got to solve for what? I've got to solve for x and y. So multiplying both sides by r cosine t is x minus h. Adding h to both sides, h plus r cosine t is x over on this side. R sine t is y minus k. So adding k to both sides, k plus r sine t is y. So now what we have is, again, remember what this was. This was a circle with a center of hk and a radius of r. That's what we've just done. So a parametric representation of a circle centered at hk with radius r is what we just have written here. So that would be x of t is h plus r cosine t and y of t is k plus r sine t. So I hope you're able to follow me. I recognize this is some fairly complicated stuff for us to work with, but I'm hoping that you can follow most of the computation. All right. So let's take a look. Let me see if you can do the following for me. So I want you to give me a parametric representation for the following equation. X minus 3 squared plus y plus 5 squared equals 16. See if you can go ahead and write up the parametric representation up on the comments. So what is x of t? What is y of t? So I'll give you a minute or so to take a look at that. So when you get your answer, please put it on the comments. While you're doing that, I'm going to take a quick look on Facebook to see if there's any news on the strike. So I think the stream should keep going. I don't see anything yet. But let's hope we hear something soon. Again, if you're in my class at 3 o'clock tomorrow, I will be in SEO 430. I'll bring another worksheet for you guys to work on. There's lots of learning assistants there to help. So it's really kind of a nice way to sort of cement some of these ideas. Got to be careful. You know, just watching me do it is not the same as having you guys do it. So if you're available, come on by tomorrow at 3 o'clock in SEO 430, and we'll take a look at this. Can I get anybody? I know there's not a whole lot of people there tonight, and I thank you for being here. So maybe I'll just go ahead and do this. The center of this problem is 3, -5. So 3 is going to stand for h. -5 is going to stand for k. Radius squared is 16, so the radius is 4. We have done the analysis. We see our formula up top. So x of t is h, 3 plus r plus 4 cos t. Y of t is k, -5 plus 4 sine t. And what we need there is we need t to range from 0 to 2 pi, by the way. 0 less equal t less equal 2 pi or less 2 pi will give us the entire circle. All right. Well, we're going to move from circles to lines. So our next example is going to require us to take a look at a line. And we'll see if we can rewrite that in a form we're more familiar with. So here we go. The example we're going to look at here is x equals 3 plus 2t and y equals 4 minus t. And I will say, note, this is a line so we'd like to express this line in the form we are used to, namely y equals mx plus b. So we go back to our same strategy. I don't know why that's happening. We'll get it to focus. We're going to go ahead and eliminate the parameter. So the parameter is t. We're going to solve for t in both sides. So I'm going to say x minus 3 here is 2t, and then divide both sides by 2. And I get x minus 3 over 2 is t. Over on this side, let's add t to both sides. Y plus t is 4, so t is 4 minus y. Okay. So we want to eliminate the parameters, so we want to go ahead and say these two things equal t, so they've got to equal each other. So x minus 3 over 2 has got to equal 4 minus y. Interesting. Let's do a little bit of arithmetic here. X over 2 minus 3/2 equals 4 minus y. Let's bring the y over to that side. Y equals 4 minus x over 2 plus 3/2. What's 4 plus 3/2? 8 and 3, 11/2. Minus x over 2. So it's almost in y equals mx plus b form. How about y equals -1/2 x plus 11/2? That should be good, and that's what I have in my notes, so I believe that is correct. Well, we haven't done a whole lot of calculus today, but we will. We'll eventually get to finding slopes of tangent lines and such, but let's continue our work with our geometry. If I give you 2 points, can we find a parametric representation of a line? Again, this becomes very important in multivariable calculus when you're doing things like Green's theorem. So, a line has 2 points. So I'm going to say given points 1, -3, which is point A, and point B, which is 0.24. Our goal is to this time find a parametric representation for this line. For the line containing A and B. Points A and B. Are we relating this to sine t and cos t? We certainly did on the circles, right? So using sine squared t plus cos squared t is 1 was our crucial identity. We'll do another problem using sine and cosine here shortly. At least that's my plan. All right, so how am I going to do this? I need a t. I need an x. I need a y. T is 0, x is 1, and y is -3. When t is 1, I'll have x is 2, and y is 4. So knowing this, can I write some kind of a parametric representation for this line? What does x of t equal? What does y of t equal? Well, x starts with 1, y starts with -3. But when t is 1, I have to get to 2. So notice, what is my change in x? My change in x from 1 to 2 is just 1, and my change in t is 1. So it behaves sort of like a slope. So how about 1 plus 1t? When t is 1, 1 plus 1 is 2. Now, what's my change in y from -3 to 4? Starting at -3, going to 4, that change is 7. And my change in t is 1. So hopefully you can see that if I do this, -3 plus 7t, now when t is 1, -3 plus 7 times 1, we're at 4. And I might as well add a couple other points, or at least one other point. If t is 2, 1 times 2 is 2, plus 1 is 3. And if t is 2, 7 times 2 is 14, minus 3 is 11. Obviously, you could write this in y equals mx plus b form. But what I'm going to tell you is this strategy of finding parametric representations for lines is what we do when we're in 3 dimensions. If you have 2 points in 3D, we will have a parametric representation, x of t equals, y of t equals, z of t equals. Again, this lesson is very much about getting you ready for Calc 3. That's when a lot of this stuff comes in. Okay. Our next example is back to sines and cosines per Maddie's question. How did you determine when t equals 0, x is 1 is what Maddie's asking me. That's where I'm starting, okay? I'm at this point 1, -3. I could have said t is 1 here and then t is 2 here, but starting at t equals 0 makes the math a lot easier, right? If t is 0, 1 times 0 is 1. If t is 0, 7 times 0 is 0. And I have x of t is 1, and I have y of t is -3. So when I'm doing this, I like to have the starting point have a value of t of 0, and the next point to have a value of t of 1. However, that's not required mathematically. You could do it another way. That's right. You assign the value that makes sense. Now, don't be ridiculous. Don't let this be t is -30 and let this be t is 500. It's not wrong mathematically. It's just kind of ridiculous. So I like to start with t of 0 and t is 1. But excellent question. Thank you. All right. Next up, what are we going to have? Again, parametric equation. X equals 3 sine t. Y equals 2 cos t. Any idea what this will be? So we'll see if anybody is brave enough to guess at what this shape will be. What do you think? Now, the problem is this is 3 and that's 2. So what's the farthest out x goes? What's the farthest out y goes? Kevin guesses parabola. Interesting guess. If we think of our ranges, right? Anybody else brave enough to guess? Maddie says hyperbola. Okay, we're getting most of the conic sections. The answer is a conic section, so that's good. But I want you to recognize sine can be 1 or -1. So the x values can go out to 3. 3 times +1. Sine is 1 when t is pi over 2. To -1, sine is -1 at -pi over 2 or 3 pi over 2. So the x values goes out to 3 or -3. Cosine, right, can be as much as 1 or -1. So cosine goes up to 2. Cosine is 1 at 0. So when y is 0, we're up here. Possibly. So maybe that gives you an indication of where this is headed. Anyway, let's go ahead and do our analysis and see what we get. So we want to eliminate the parameter, and then we will look at finding the slope of the tangent line. So first off, let's go ahead and do our work. X over 3 is sine t. Y over 2 is cos t. And then we remember our favorite identity. What is our favorite identity? Cos squared t plus sine squared t is 1, and we're not focused again. I don't know why. There we go. So cos t squared, that's y over 2 squared. Plus x over 3 squared is 1, and maybe you're starting to recognize this pattern. Y squared over 4 plus x squared over 9 equals 1. What is this? This is an ellipse. So we had answers that were focused on conic sections. That was good. Indeed, these things often are conic sections, and this is what that looks like. Okay, so we were able to successfully identify that. We have eliminated the parameter, but now this is the question I want to ask next, namely, find the slope of the tangent where? At the point t equals pi over 4. Now, what is that? So we can identify where that is on our graph and maybe eyeball it, give ourselves a guess, and then check. So if t is pi over 4, x is 3 sine pi over 4, which is 3 root 2 over 2. And y is 2 cos pi over 4, which is 2 root 2 over 2, which of course is root 2. Just get some decimal approximations. I just want to visualize it if I can. 3 times the square root of 2 divided by 2 gives me 2.12. And root 2 I know is about 1.414. So x is a little bit more than 2, y is a little bit more than 1. So looking at our picture, that's approximately where we are. Now the slope of the tangent line, want to give it a guess? Something like that. It's certainly negative. Maybe -1, maybe -0.5, somewhere in that range. So we need a strategy to actually be able to determine the slope of that tangent line. So we're going to go back to the top of our page here. We have x is 3 sine t. We have y is 2 cos t. The question is, what is the slope of the tangent? The question is, what is dy dx? So let's look at this. And we're interested at pi over 4. Again, our question is, find the slope of the tangent. At t equals pi over 4. And again, we have x is 3 sine t. y is 2 cos t. But the slope of the tangent is what in calculus? The slope m is, of course, dy dx. Now, I could eliminate the parameter and find dy dx, but I already have t here. So I'm actually going to use t to help me do this. So the slope will be not dy dx, but dy dt divided by dx dt. So look at that for a second. Dy dt divided by dx dt. If you would think of these things as regular fractions, that would reduce to dy dx. Very nice. So I've got to find what dy dt is. I've got to find out what dx dt. Again, y is 2 cos t. So the derivative of y with respect to t is 2 times the derivative of cosine is negative sine t, which would give me negative 2 sine t. So the dy dt that I have here is negative 2 sine t. I've also got to do this for dx dt. Can I do this for dx dt? Let's see what we get. So I've got x is 3 sine t. So dx dt, the derivative of x with respect to t is 3 times the derivative of sine t, which is cos t. So what I've done is I've determined the slope of the tangent line for any value of t. I've got m is negative 2 sine t over 3 cos t. So that'll be important for me to use. So we'll say the slope of the tangent at t equals pi over 4 will be the slope at t equals pi over 4, which will be negative 2 sine pi over 4 over 3 cosine pi over 4. And you know sine of pi over 4 and cos pi over 4 are the same thing. Root 2 over 2, 3. Root 2 over 2, those divide out nicely, and I get negative 2/3. Let's go back and take a look at our graph. Do you recall at the top of this page, we had a hand-drawn ellipse, and we tried to approximate what that would be. Does that look like that slope could be somewhere around negative 2/3? In fact, our guess was either -1 or -0.5, and negative 2/3 is in between those two. So that makes me feel pretty good about my initial guess. All right. Let's go ahead and do one more problem in that realm. I think we have time. Yes, I think we do. So we're going to look at the following. We're going to look at x equals 2 plus natural log t, and y equals 3 plus the square root of t. The first thing I like to do often is to eliminate the parameter, and then we'll find the slope of the tangent somewhere. So can I eliminate the parameter? Well, let's solve for t if we can. X minus 2 is natural log t. Remember, the base of the natural log is e. So e to the x minus 2 equals t. And then what can I do? Then I can go ahead and just plug that in over here for t. So I can say y equals 3 plus the square root of e to the x minus 2. That's not bad. You certainly could do it. I could leave this as the answer. I could say y minus 3 is e to the x minus 2. I could square both sides, but you got to be careful. If you square both sides, you could be adding more stuff. So I think I'll leave my answer in that form. And then the last question we'll do today is we will find the slope of the tangent at t equals 1. So we need dy dx is dy dt over dx dt, as we saw in our last example. So let's remind ourselves of that. Dy dx, slope of the tangent, is dy dt over dx dt. So I will need to get dy dt and dx dt. So x is 2 plus natural log t. Dx dt, the derivative of 2 is 0. The derivative of log t is 1 over t. So we'll go ahead and put that in the denominator in the bottom. 1 over t is there. What is y? Y is 3 plus the square root of t. Remember what that means. So we'll say y is 3 plus t to the 1/2. How about dy dt? Dy dt is 1/2 t to the negative 1/2, which is 1 over 2 t to the 1/2, which is 1 over 2 root t. That goes on top. So 1 over 2 root t divided by 1 over t. 1 over 2 root t divided by 1 over t. 1 over 2 root t times t over 1, which is t over 2 root t. And we want to know what the slope of the tangent is where. What is the slope of the tangent at t equals 1? Steal some room here on my page. So the slope at t equals 1 would be t over 2 root t at t equals 1, which is 1 over 2 root 1, which is 1/2. So the slope of the tangent there would be 1/2. All right, friends. Well, I think that's about all I want to talk about today. So what did we do? Started off with a brief review of the Maclaurin series. Remember, you should memorize e to the x, cosine x, and sine x. I showed you most of the proof that e to the ix is cos x plus I times the sine of x. That's a really nice rule to have, in your bag of tricks. Then we began our discussion on parametrics. We defined what parametric equations are. We eliminated the parameter. We looked at several examples, and we finished off by finding slopes of a tangent, remembering, of course, that dy dx is dy dt over dx dt. I sincerely hope this is our last video lecture. I think they're getting close to settling the strike. So I hope that I will see all of you in class on Monday. And tomorrow, if you're available at 3 o'clock, come by SEO 430. I'll have a worksheet for you to work on. And like I said, the learning assistants will be there to help. Thanks so much for coming to the live broadcast. And I look forward to seeing you in person soon. Ciao.